If you have watched the earlier clips of this series, you are aware that galactic rotation curves are naturally explained by an elongated cylindrical-like source and why. In this video, we are going to explore some further observational consequences. First, an obvious one. Whatever dark matter is, its distribution would be peaked along the polar galactic regions, with little to be found in the galactic plane beyond the disk. Next, a less obvious one. Remember from video 2b the celebrated Tully-Fisher relation that relates the asymptotic flat velocity of objects in galactic orbit, that's something controlled by the dark matter distribution, with the total luminous ordinary matter of the galaxy. This empirical relation is quite a surprise, as it implies a proportionality of visible and dark matter, which are in principle supposedly independent fluids with very weak interaction. Let us see how this comes about in a scenario with dark matter filaments. We saw already that the asymptotic velocity is proportional to the square root of the cylinder's linear mass density. Now, imagine two neighboring cylinders of possibly different dark matter linear densities. Ordinary matter lying somewhere in that region will fall either towards one or the other. Now, because the force is proportional to lambda divided by r, remember, everything happens as if there was one less dimension than in the ordinary Newtonian mechanics, where point sources have 1 over r squared, falling gravitational fields. Well, then the point where the forces of the neighboring cylinders or filaments are equal is closer to the less dense filament. Therefore, one expects that each filament swipes the conventional visible gas in an area of radius lambda around it. That area is then proportional to lambda squared, and therefore the luminous mass is proportional to v to the fourth, because of the square root we mentioned a moment ago, 2 powers of the velocity for each power of the linear density. The total visible mass that falls to this one cylinder is therefore proportional to the 4th power of the velocity, which is a form of the Tully-Fisher law. This exponent would be different if applied to a spherical distribution of dark matter over densities of spherical shape. If one can come up with a scheme in which there is a flat asymptotic velocity, which is not natural with spherical distributions. So 4 comes out naturally with filaments, 4 can be tuned with spheres. Now 4 is exactly obtained within Mond, because it effectively achieves a dimensional reduction. So let's give credit where it's due, and now ask ourselves whether anybody has actually seen such filament. The answer is definitely so. Here is as an example an image by the Sloan Digital Sky Survey, where you can see that galaxies are not placed in a homogeneous pumpkin soup, but rather distributed like pumpkin hairs along stretches of matter separated by voids. To orient you in this type of picture, you should note that the Real Madrid Stadium is in the center, and the outward radius is redshift, a proxy for the distance to that stadium at which each galaxy can be found. Now, at a scale of 40 megaparsecs, large-scale computer simulations do show such a cosmic web of dark matter, with the same filamentary void structure distribution for dark matter. It is at the smallest scale that they have focused on the formation of spherical halos, and people have not realized that very prolate structures do actually explain rotation curves of spiral galaxies better. We're at this time carrying a statistical analysis with a large sample of galaxies at the University of Madrid. Now, even if dark matter does not carry electric charge, and therefore does not couple to light, shouldn't we be able to kind of see these filaments with gravitational lensing? That is, they're bending the light beams from other conventional matter sources when the beams pass the dark matter gravitational field. I do not know of any one definite sighting, but here is statistical evidence. This group took pictures with galaxy pairs and rescaled them, so the distance from center to center in this picture is always the same. The exercise is then to stack pictures with pairs of neighboring galaxies on top of each other. That is the top picture here, and there we go. We can see a bridge of dark matter, seen by lensing, extending from one to the other galaxy. Statistically, there is indeed a filament extending from galaxy to neighbor galaxy. In the bottom plot, they have shown what appears if you look at galaxies that are not near neighbors. Nothing. Indeed, there's no reason for galaxies far away from each other to show a matter correlation of this sort. The respective filaments can extend left for one and top for the other, or outwards of the screen, and on average, there is nothing special in the direction linking them. Now these people try to carry an analysis of the mass in this bridge, and one can get 1.5 times 10 to the 13 solar masses. That is, 10 times the mass of the Andromeda Galaxy, for example. So these filaments can hold a large fraction of the total dark matter that cosmology requires. And, as I showed in the earlier video, Explain the flatness of rotation curves. That's just my hobby these days. Sorry for repeating it. Moving on, how is the motion of matter in the presence of such filamentary gravity sources? You know, the answer from electromagnetism is easy. When you have a magnetic field, trajectories are helicoidal along the field lines. The same happens here, because there is translational invariance along the cylinder, except that because of the equivalence principle, all mass follows those helices, not just charged particles, but also neutral atoms or molecules, or even stones or stars. You know that charged particles in such trajectories emit synchrotron radiation. I will flash a few of the relevant equations in case you need to look them up. But the radiation is only large if the filament is very thin respect to the galactic scale. The power emitted is proportional to the fourth power of the velocity, and this is non-relativistic, as we saw earlier, at most 10 to the minus 3 of the speed of light. So you really need small radii here in the denominator to get appreciable power. But the shape of the rotation curves is suggesting that the filament has a thickness well comparable to the galactic size, so synchrotron radiation should be probably undetectable. As an aside, many galaxies are of course showing synchrotron jets, such as this famous M87 galaxy, whose central black hole was mapped out last year, and while rare, there are a few spiral galaxies showing such jets too. Another phenomenon that you can expect when you have helicoidal motion along the field lines is an aurora borealis at the poles, where the lines converge. Something similar could happen at the poles of a galaxy where the filaments arrive. Since matter can move at low energy cost along them, they can act like conveyor belts. Well, in our galaxy seeing gamma rays, there are two bubbles of radiation at the galactic poles, discovered by the Fermi satellite. Wouldn't it be interesting if they were caused by matter falling in, as opposed to matter being radiated out of the galactic center? I don't know. We will continue this what-if physics discussion in the next clip.